There is a fact which I have carried with me for some years now, and which seems to me to grow heavier rather than lighter with the passage of time, as certain facts do when their implications are allowed to unfold fully in the mind. The fact is this. We have known how to create a star on Earth since November 1st, 1952. Not a metaphorical star, not a poetic approximation, not a figure of speech, but the actual thermonuclear process by which the sun and all the stars in the visible universe produce their energy. The fusion of hydrogen into helium at temperatures of tens of millions of degrees, releasing energy according to Einstein's relation between mass and energy. This process, which has powered every star that has ever shone since the first galaxies coalesced from primordial gas roughly 13 billion years ago, was reproduced by human beings on a coral atoll in the Marshall Islands called Elugelab. The device was called Ivy Mike. Its yield was 10.4 megatons, 10,400,000 tons of TNT equivalent. The island of Elugelab, approximately 1 mile in diameter, ceased to exist. In its place was a crater 2 miles wide and 160 feet deep, filled with seawater. We had created a star, and we had used it to erase an island from the map. I opposed the development of the hydrogen bomb. I should say this plainly because the record is public, and because I have no interest at this point in disguising my position or the consequences it brought upon me. I opposed it in committee. I argued against it before the General Advisory Committee of the Atomic Energy Commission in October of 1949, and I signed a report, along with Enrico Fermi and Isidore Rabi, among others, that called the hydrogen bomb a weapon of genocide and recommended that the United States commit to never developing it. For this, and for other things, for associations that were deemed suspect, for friendships that were deemed dangerous, for the sin of having been right about a question that powerful men wished to answer differently, I was subjected in 1954 to a hearing that stripped me of my security clearance and ended my involvement in the affairs of government. I do not say this to invite sympathy. I say it because it bears on the question I wish to examine. The question of what it means that we can create a star and that 70 years later we still cannot control one. Let me be precise about the physics, because the physics is beautiful. Perhaps the most beautiful physics I know, and because the beauty is part of the problem. The sun, our sun, an ordinary main-sequence star of spectral type G2V, produces its energy through a process called the proton-proton chain. At the sun's core, where the temperature is approximately 15 million degrees Celsius, and the density is roughly 150 grams per cubic centimeter, about 13 times the density of lead, hydrogen nuclei, which are simply protons, are compressed together with sufficient force to overcome the electromagnetic repulsion between their positive charges. This repulsion is enormous. 2 protons, each carrying 1 unit of positive charge, repel each other with a force that increases as the inverse square of the distance between them. At nuclear distances, roughly 1 femtometer, 10 to the negative 15th meters, this repulsion amounts to approximately 230 newtons, which is, for a particle of such minuscule mass, a stupendous force. Under ordinary conditions, no 2 protons would ever come close enough to interact via the strong nuclear force, which is attractive, but operates only at these very short ranges. But the sun has 2 resources that we on Earth must struggle to replicate. The first is gravity, the crushing weight of 600 billion kilograms of matter pressing inward from all directions, generating pressures at the core of approximately 250 billion atmospheres. The second is time. The proton-proton chain is, by nuclear standards, extraordinarily slow. The first step, the fusion of two protons to form a deuteron, a positron, and a neutrino, requires one of the protons to undergo an inverse beta decay at the precise moment of closest approach, converting from a proton to a neutron through the weak nuclear force. The probability of this happening in any given collision is fantastically small. A typical proton in the sun's core waits, on average, approximately 1 billion years before successfully fusing with another proton. 1 billion years. The sun can afford this patience because it has an effectively unlimited supply of protons, and because it has been burning for 4.6 billion years and will continue for roughly 5 billion more. It is, in the most literal sense, a controlled fusion reactor, controlled by gravity, sustained by patience, and operating on a time scale that is, from a human perspective, indistinguishable from eternity. We do not have gravity. We do not have patience. And so the path to fusion on Earth must be, by necessity, entirely different from the path the sun takes. And here one begins to understand the nature of the difficulty, a difficulty that is not merely technical, though the technical challenges are formidable, but that touches on something deeper about the relationship between human ambition and natural process. The reaction that is most promising for controlled fusion, the reaction that every major fusion experiment in the world, from the tokamaks of the 1960s to the ITER facility now under construction in southern France, has been designed to exploit, is the fusion of deuterium and tritium. Deuterium is hydrogen with one neutron added to its nucleus. It occurs naturally in seawater at a concentration of roughly 1 part in 6,400 and is, for practical purposes, inexhaustible. Tritium is hydrogen with two neutrons. It is radioactive, with a half-life of 12.3 years, and must be bred from lithium in a nuclear reaction. When a deuterium nucleus and a tritium nucleus fuse, they produce a helium-4 nucleus, an alpha particle, carrying 3.5 million electron volts of energy, and a free neutron carrying 14.1 million electron volts. The total energy released per reaction is 17.6 million electron volts. This is roughly 4 times the energy per reaction of uranium fission, and it comes from fuel that is in principle available in the ocean in quantities sufficient to power human civilization for millions of years. The numbers are seductive. I use that word deliberately, because seduction is what they accomplish. They seduce the mind into believing that the problem is nearly solved, that the fuel is there, that the reaction is understood, that all that remains is engineering. And engineering, as every physicist knows, is what happens after the physics is settled. But the physics of controlled fusion is not settled. It has not been settled for 70 years. And the reason it has not been settled is not because the physicists have been idle or incompetent. Some of the finest minds I have known have devoted their careers to this problem, but because the physics itself is, in a word that I do not use lightly, adversarial. To fuse deuterium and tritium, one must heat the fuel to approximately 150 million degrees Celsius, 10 times hotter than the core of the sun. At this temperature, the fuel exists as a plasma, a state of matter in which electrons have been stripped from their atoms, leaving a gas of charged particles that is governed not by the relatively simple laws of ordinary gas dynamics, but by the deeply complex equations of magnetohydrodynamics. A plasma at 150 million degrees cannot touch any material wall. There is no material that can withstand such temperatures. The most refractory substances known, tungsten and carbon composites, melt at roughly 3,400 and 3,500 degrees Celsius, respectively. The plasma must be confined by other means, by magnetic fields in the tokamak approach, or by the inertia of its own compression in the approach we call inertial confinement. The tokamak, a Russian word, an acronym derived from the Russian for toroidal chamber with magnetic coils, was conceived in the early 1950s by Andrei Sakharov and Igor Tam. Sakharov is a man whose trajectory through life bears, I think, certain uncomfortable resemblances to my own. A brilliant physicist who helped create his nation's thermonuclear weapon and later became its most prominent dissident, who understood both the beauty of the physics and the horror of its application, and who paid a very personal price for insisting on that dual understanding. The tokamak confines the plasma in a donut-shaped, toroidal chamber using powerful magnetic fields, typically generated by superconducting coils carrying currents of tens of thousands of amperes. The magnetic field lines spiral around the torus, and the charged particles of the plasma follow these field lines, orbiting endlessly without, in principle, touching the walls. In principle. In practice, the plasma does everything in its power to escape. This is not anthropomorphism. It is physics. A plasma at 150 million degrees is, from the standpoint of energy density, one of the most extreme states of matter that can exist on Earth. It is turbulent, unstable, and subject to a bewildering array of instabilities: kink instabilities, sausage instabilities, ballooning modes, edge-localized modes, neoclassical tearing modes, each of which represents a different way in which the plasma can distort the magnetic field that confines it, find a path to the wall, and dump its energy into the surrounding structure in a burst that can damage or destroy the containment vessel. The study of these instabilities has occupied some of the best plasma physicists in the world for decades. Each one, when understood and suppressed, reveals another behind it, like the heads of the Hydra in the Greek myth. You cut one, and two more grow in its place. And here one arrives at what I think is the central irony of the fusion problem, an irony that carries for me a particular moral weight. We solved the uncontrolled problem in less than 7 years. From Teller's first serious calculations in 1946 to the Ivy Mike test in 1952, we went from concept to detonation, a thermonuclear yield of 10.4 megatons, achieved by using a fission bomb to compress and heat a cryogenic mixture of liquid deuterium. The Teller-Ulam design, as it came to be known, and here I must note with what precision I can muster that the design involved contributions from many people, including Stanislav Ulam, whose key insight about radiation implosion made the device possible, and Marshall Rosenbluth and Konrad Longmire, and others who performed the calculations. The Teller-Ulam design solved the problem of achieving fusion conditions by the simplest possible method: overwhelming force. If you detonate a fission bomb adjacent to a container of fusion fuel, the X-rays from the fission explosion compress and heat the fuel to the required conditions in a matter of nanoseconds. The plasma does not have time to develop instabilities. The confinement is provided not by magnetic fields, but by the inertia of the fuel itself. It fuses before it can fly apart. The whole process takes less than a microsecond. This is the brute force solution. It works. It has worked every time it has been tried, from Ivy Mike to the largest devices ever tested, the Soviet Tsar Bomba, which yielded approximately 50 megatons in October of 1961, the largest explosion ever produced by human beings, a yield equivalent to roughly 10 times the total explosive force of all the ordnance used by all sides in the entirety of the Second World War. It works because it does not require control. It does not require confinement. It does not require the sustained, delicate, minute-by-minute management of a plasma that wants nothing more than to fly apart and destroy whatever is containing it. It requires only the willingness to release an enormous amount of energy in an enormously short time, with no regard for what is destroyed in the process. The controlled problem, the problem of sustaining fusion reactions at a steady rate, extracting the energy as useful heat, converting it to electricity, and doing so for months and years rather than microseconds. This problem is, by comparison, almost incomparably harder. And the reason, I think, is not merely technical. The reason is that control and destruction draw on fundamentally different relationships with nature. Destruction is simple. You do not need to understand turbulence to create a fireball. You do not need to solve the magnetohydrodynamic equations to design a weapon. You need only to create the conditions, briefly, violently, without concern for sustainability, and the physics does the rest. But control requires understanding. Control requires that you know not only how to initiate the reaction, but how to sustain it, how to manage the instabilities, how to extract the energy without destroying the vessel, how to replace the fuel, how to handle the neutron flux that degrades the structural materials, how to breed the tritium that the reactor consumes, how to maintain the superconducting magnets, how to deal with the disruptions, sudden losses of confinement that dump the entire thermal energy of the plasma, sometimes tens of millions of joules, onto the wall in milliseconds. The ITER project, the International Thermonuclear Experimental Reactor, now being assembled in Cadarache, France, by a collaboration of 35 nations, represents in some sense the culmination of 70 years of effort. It is designed to produce 500 megawatts of fusion power from an input of 50 megawatts of heating power, a gain factor which we call Q of 10. If it achieves this, it will be the first fusion device in history to produce more energy than it consumes. The plasma volume will be 840 cubic meters. The magnetic field at the center of the plasma will be 5.3 Tesla, generated by superconducting niobium tin coils, cooled to minus 269 degrees Celsius, just 4 degrees above absolute zero. The temperature of the plasma itself will exceed 150 million degrees. In a single machine, separated by a few meters of engineering, the coldest and the hottest conditions achievable by human technology will coexist. There is something in this that strikes me as a kind of parable, though of what exactly I am not certain. ITER was originally proposed in 1985. It is now expected to achieve first plasma sometime in the early 2030s, and full deuterium-tritium operations perhaps a decade after that. The project has cost, at last estimate, somewhere in excess of $25 billion. It is the most expensive scientific instrument ever built. And it is, by design, an experimental reactor. It will not generate electricity. It will demonstrate that controlled fusion is possible. The power plant, the device that actually produces electricity from fusion, is a further step, requiring solutions to problems that ITER is designed to identify, but not to solve. The tritium breeding blanket, the materials that can withstand 14 mega-electron-volt neutrons for years without catastrophic degradation. The plasma-facing components that can endure the heat flux. The remote maintenance systems that can operate in a radioactive environment where human access is impossible. I have been wrong about many things. I was wrong to believe in the years immediately after the war that the international control of nuclear energy would follow naturally from the shared recognition of its dangers. I was wrong to believe that opposition to the hydrogen bomb could succeed through reasoned argument alone, without the political power to enforce that argument. And I think it is possible. I say this with the humility of a man who has been wrong often enough to distrust his own certainties. That I was wrong to believe that the gap between what we can destroy and what we can build is a permanent feature of the human condition. Perhaps it is not. Perhaps the fusion reactor will be built, will work, will provide energy to a world that desperately needs it. I hope so. But hope is not prediction, and the history of fusion, the long, humbling, instructive history of a problem that has resisted the best minds of 3 generations, counsels caution. There is a concept in Indian philosophy. I encountered it through the Vedas, and it has stayed with me. The concept of tapas, which means, roughly, the creative heat generated by ascetic discipline. The idea is that creation requires sustained effort, sustained sacrifice, sustained attention, that the universe does not yield its gifts to those who demand them, but to those who earn them through patient and devoted work. The sun performs its fusion through tapas, through the patient gravitational compression of its core over billions of years. We who lack patience, who demanded fusion in microseconds for the purpose of destruction, who now ask for it in sustained, controlled form for the purpose of creation, we must learn, I think, a different kind of tapas. Not the violence of implosion, but the discipline of confinement. Not the brute force of Ivy Mike, but the delicate, sustained, minute-by-minute management of a plasma that does not wish to be managed. There are children playing in the streets who could solve some of my top problems in physics because they have modes of sensory perception that I lost long ago. And I wonder sometimes whether the solution to controlled fusion, if it comes, when it comes, will come not from the generation that built the bomb, not from the generation that inherited the bomb, but from some future generation that has learned to think about power differently, that has learned to approach the problem of sustaining a star, not with the urgency of war, but with the patience that the physics demands. The optimist thinks we will have fusion power in 30 years. The pessimist fears that we have been saying this for 30 years. Both are correct, and this is perhaps the most honest thing that can be said about the state of the art. But I would not have you think that the delay is merely a failure. It is also a lesson, the deepest lesson that physics has to teach, and one that I learned too late and at too great a cost. The lesson is this: destruction is easy. It is easy because it requires only the release of energy, the breaking of bonds, the dissolution of order into disorder. The second law of thermodynamics is on the side of destruction. But creation, sustained creation, controlled creation, the building and maintaining of complex, ordered structures against the tide of entropy, creation is hard. It is the hardest thing in the universe. It is what the stars do, burning steadily for billions of years. It is what life does, maintaining its improbable order against the constant pressure of dissolution. And it is what we must learn to do if the fire that we have stolen, or perhaps I should say the fire that we have made, which is in some ways a more troubling formulation, if that fire is ever to warm rather than burn. I said once, speaking of the atomic bomb, that the physicists have known sin, and that this is a knowledge which they cannot lose. The hydrogen bomb deepened that sin, extended it from the fission of heavy elements to the fusion of light ones, from the splitting of the atom to the forging of the nucleus, from the bottom of the periodic table to the top of the stellar energy curve. We have known since 1952 how to create a star. The knowledge is ours. It cannot be taken back, any more than the fire could be returned to Olympus after Prometheus had carried it down. But knowledge, as I have had occasion to learn, is not the same as wisdom. Knowledge tells you how to create the conditions for fusion. Wisdom tells you whether to do it in a microsecond or a millennium. Knowledge tells you the cross-sections, the temperatures, the confinement times. Wisdom tells you what it means for the people who will live with the consequences, for the world that will be shaped by the choices, for the long future that will judge us not by what we knew, but by what we did with what we knew. Both the man of science and the man of action live always at the edge of mystery, surrounded by it. The mystery of fusion, why we can destroy with it but not yet build with it, why the uncontrolled reaction was achieved in 7 years and the controlled reaction has eluded us for 70. This mystery is not, I think, a mystery about physics alone. It is a mystery about us, about what we find easy and what we find hard, about the relationship between power and patience, between urgency and discipline, between the desire to command nature and the willingness to learn from it. I do not know when we will have controlled fusion. I do not know if the tokamak is the right path, or if some other approach, inertial confinement, stellarators, magnetized target fusion, something not yet imagined, will prove to be the answer. I know only that the question is worth asking, that the pursuit is worth sustaining, and that the answer, when it comes, will tell us something about ourselves that we very much need to know. It will tell us whether we are capable not only of releasing the energy of the stars, but of holding it, gently, sustainably, for the long benefit of all, in the imperfect and beautiful vessels of our own making. Science is not everything, but science is very beautiful, and the star, when we learn to hold it, will be the most beautiful thing we have ever made, not because of the temperatures or the pressures or the engineering, but because it will mean that we learned at last that creation is harder than destruction, and chose creation anyway.